Okay, so let's haul off and work. So what we've got. Oh, I didn't even do that. Um, open it. Come on, come on. See, it's trying to reach over to the library. It's having trouble. Oh, come on. There we maybe go. Okay. Okay. So what we have is we have really two sets of things to do. We have energy problems, and then we have impact. So what I might do is go work some of these over the next couple days, because those are the new things. This energy stuff, those are the easier problems. So let me pick up some impact ones. And I think I'm in the wrong section. I need to move forward, but it's kind of hard to move. It's hard to draw the bar down and see where you are. Here, let's start with impact. Let's just do some of these initial ones. Okay. Well, we'll start with these F ones. Okay. Well, there you go. So half kilogram ball strikes a rough ground. Hang on. Let me get this and grab it. Put it over here. Wait a minute. Let me put it in here. I'll just drop it here. How's it doing this? I guess good enough. I don't have time to figure out what it's doing. It says a half kilogram ball strikes a rough ground and rebounds in the velocity that's shown. Determine the magnitude of the impulse that the ground exerts on the ball, assuming the ball doesn't slip when it strikes the surface. Okay, when it strikes the ground, and neglect the size of the ball. So he wants to know that impulse. So that impulse is this. He defines that as the impulse. So really all you're looking at is let me go back to the original definition. So the way the initial original definition looked like was this. And then this dt got drug over to the right. And then he decided to define this as a thing called the impulse. So if you look at the left, it's this. So this would be from, I'll say, initial or before the impact and after the impact. Now, what'll happen to you in thermo is they'll say initial and final. It's a little bit more associated with energy, but let's take a look at that. So what happens is only a certain portion of this hits the ground. The other part's going to the right, and this other part should be maintained, but I don't even care. I'm just interested in this component and that component. So if I look at that, this component is just 25 over square root of 2 because it is 45. This one is not. This one is actually 10. Okay, so if you take a vector here, length of 10, you're looking for this one, which is 10 sine of 30, which I think that's supposed to be about 5. So you got, okay, so let's take a look at this and be real meticulous. Okay, I don't know what that number is, but I didn't start MATLAB, but I can. Let me start it. It'll make it in a minute. Or maybe it won't. Well, in any case, so let's define these. So I've got one that is 25 over square root of 2, and I'll replace that with the number in a minute. And the other one's 5. First thing is, this one can't be larger than that one. If it was, then you haven't obeyed the laws of physics. Okay, let me get rid of all this other mess. Okay, so what is 25 divided by the square root of 2? Uh-oh. I said that. Wait, 17. It went away. Okay, and 2/3, but here. How about, well, okay. How about just saying that? And so um, in these, there you have to remember there are vectors. So when you look at this, the impulse, okay, so I'm basically drawing this down. The impulse is equal to mv, and I don't know if I want to call it 2 or final, but he's always calling it 2, so I better just stick with that. V1. Now, they're associated a vector with this, so that means that what was the m there? So it's 0.5, and I'll say v2 minus v1. So if I can, okay, let me get that thing out of the way. So I'll say I've got to choose a positive direction, I guess, and I don't know which way to choose. The answer in the back might have a different sign because he might have chosen a different direction. I don't really know, but what you'll end up with is a half times, okay, V2, which was this one. Okay, that's a -5, and then the minus, okay, 17.67. Half of that. Okay, well, all right, so let's do it like this. I'll add up to it, and then I would just go ahead and divide it by 2 because that gives it that. So 11. Now mine has a minus sign, 11 point something, 3, 4. I mean, that's good enough. Now let's see how, okay, F15-1, and it's on page 229. Let's see if I can drag myself all the way down there. What did I say? 1550. Okay, I'm in the wrong one. Okay, so okay, well, I'm not going to do the other one. So I only did the one in the Y. So 11.3. Oh, why am I clicking there? 11.39? I got 11.34. Or am I misreading it? Oh, yeah, 11.34. So I didn't do I'm not going to do the other one. So, and then he went ahead and did the X because of the friction, but I'm not going to do that one. So I'm only doing the one in the Y. So that's okay. It's not that I don't want to do the other one, but I don't. So, and I guess I should, but I'm not going to. So let's go look at another one. Okay, so we talked about that one. Let's see. Here we go. We'll do this one. So let's grab this one. And then, or is there a better one down in the book somehow? Let's see if there's a better one. Something more interesting. Crate weighs 50 pounds. They start from S, determine the speed after, so the force exerted by crate A on B during the, that's interesting, moderately interesting. I don't know. I don't see anything that's any more interesting than anything else. Oh, here's one. This one has a funny cable connection, so let's do that one. Okay, so it says determine the velocity of each block after 2 seconds. Okay, so I start back at this, and I'll draw each one of these separately, but and so what you could do is some of the forces actually and do this dt integration. If you look at this and all of the forces that are on these blocks, they don't change with respect to time. So if I grab a particular block, and I think I could probably do this reasonably well, and that is grab both blocks at the same time and then copy them down underneath here and say, this is a tension, that's a tension, that's a tension, this is 10 pounds, that is 50 pounds. So if I look at the block to the right, or B, basically I get sum of the forces, and I'll just call it in the Y, times delta T. So here, this should be stated like this. So this is a vector, that's a vector, and that's a vector. So in my particular case, I'm just doing it only in the Y. Okay, so I think he said they're released from rest. So velocity of A initial equals to the velocity of B initial equals to 0. But I'll write him down anyway. So here, mv2 minus mv1. But now I'm going to apply it to A, and then I'm going to apply it to B. So I guess I'll draw a line down here. Look at what I have to say. In A, I'll make both of them be positive or be up. So on A, I'll look over here at block A. I make positive up. I see 2t minus 10 for the forces. Now, he says 2 seconds. So I'm going to assume that T1 is equal to 0 and T2 is equal to 2. So therefore, the change in time is just 2 seconds. So that means this in both problems is going to be 2. So I get 2. And now I look at the right side. If I look at the right side, all of the initial velocities are 0. So all I get is the mass, which in this case on the left is 10 over 32.2. That's the mass of block A right here. And then times the velocity of A at time 2. Then I go over here and do it to B. I'll see 1t. So I'm looking at this one, minus 50. Mass of this thing is 50 over 32.2. And I'm looking for velocity B at 2. So I got 2 equations, which I guess I should have drawn a line there. But however, let me go one more step and put those numbers down. I can take the 2 and slide it back underneath. I forgot the 2 right here, because I still have to carry the 2 seconds here. I can put the 2 underneath, and I can have 2t minus 10 equals to, in this case, 5 over 32.2, VA2, t minus 50 equal to, and I guess 25 over 32.2, VB2. And I guess I could just hold up and say these are the 2 equations I'm going to deal with. Now I've got to deal with how the 2 velocities relate to each other. Say SA, draw this little thing, SB. Wonder if I could do something like this. Here, let me try some. Slide the whole problem to the right. Look at that. Now, I can say the length of the rope equals 2. And I'll say this is part of the rope too. 2SA plus SB plus any sort of parts that are sitting over the pulleys like that part that don't count as far as a time change. So what you're going to get is you're going to get 0 is equal to 0, that's a 0, 2 SA dot plus SB dot. And so now two things happen. One, both of these are positive down, but over here, both of them are positive up. So what you find out is that 0 is equal to 2 VA plus 1 VB. So you go in here and you realize that you can basically replace one with the other. It's kind of up to you. What did you want to know? Determine the velocity of each block. So we're more interested in the velocities than we are than the tension. So let's try to get rid of the tension. So what I'll do is I'll write this down. 2t minus 10 equals 5 over 32.2 VA2. I'll take this equation and slip under it, but I'll multiply it times 2 as I go through it. If I multiply it times 2, 50, 32.2. This time I'll replace VB, and the printout is too small, too large. If I look over here, VB is equal to, move that over to the other side, minus 2 VA. Did I hit the keyboard wrong? I guess I'm okay. And that's because of the way the ropes are. So if this one was going up at 2, this would be going, well, if this was going up at 1, that would be going down at 2. So what I'll do is I'll erase this and replace it with minus 2, and I'm replacing B with A, VA2. Now what I can do is just subtract these. So I could go in, change the signs all the way across, and then add them. So I get, I don't know why it jumped. I get 100 minus 10's 90. Then I've got to look at all this. Okay, so I've got 100, 105, I think, over 32.2 is equal to 2 VA or VA2. And unless I made a mistake, which is very possible, 90 times 32.2 divided by 105. For some reason, I don't know. Okay. VA2 is equal to 27.6. That's what I get for VA2. Now let me go check. Okay, wait a minute. 15, was it 19? 19 on page 233. It's hard to jump around. 15, 19, 15, 19. I don't know what those R's are. Okay, why am I not seeing it? Oh, here it is. Okay, I got VA. Okay, so VA 27.6. I think that's what I got. VA 27.6. And so I'm tired enough that I'm not interested necessarily in finding the other, but I guess I should. So if I did, I could basically say, okay, now see, I've got VA being positive, and positive kind of means that, so that means it's going up. Is that what he got? VA was going up at 27. Oh, wrong button. And since this is the case, this comes together that shows me VB is equal to twice that, 50, well, 55. Why did I say, is that right? Here, 55.2 here. Now I'm going to be really lazy. So since that's the case, I can grab that equation and come back to this one. So what's ironic about this is, if you really look at this, this is nothing more than sum of the forces equal mass times acceleration if the acceleration were constant. And in this particular case, that is. So all you're doing is you're just bringing the delta t over right like that. Let's see, 233. Let's go on. Whoop, I don't have that. Come on. Let's go down and look at a harder one. Or let's go on. Let's see. What do we have now? Oh, conservation of a bunch of things together. Let's do one of these. These F ones here. Get rid of this. Going. I don't know. Here. Blocks A and B. Let's see. Mass defined is the stationary. Okay. And the blocks coupled together after the impact determine the maximum compression of the spring. Here we go. Good enough. Do that one. So if you go in, start yourself a new page. Okay, stop it. Okay, so what you got is two phases of this. First phase is right at the impact. So this is your system. Okay, so they're before impact. What this is there's, before that spring happens, there's no internal forces or no external forces pushing on these two masses. This one's just sliding to the left. And as a result, what you find out is there's no, let's go back up here, and what you'll find out, the equations are derived or set such that, all the way up here, so that you have this. A system of equation where there's no external forces put on the system, like a tennis ball drop hit the ground. You're not hitting the tennis ball the second it hits the ground. It's hitting the ground, so to speak. So if you go back and look at it, the equations are basically, and there's A and B, so I'll say mass A, velocity A, say initial, plus mass B, velocity B initial is equal to mass A, velocity A final, or 2, plus mass B, velocity of B final, or 2. It says this little hook somehow couples them together, which means the velocity of A2 is equal to the velocity of B2 because they're stuck together. And when they're stuck together, I'll just go ahead and grab this thing and redo it. Mass A, velocity A initial, mass B, velocity B initial equals 2, and I'll just sum them. MA plus MB times, I guess I'll just say 2, since I don't really want to designate it A or B. It's just everything. So he tells us, okay, what does he tell us? A is stationary. B is moving at 15. Now, here's where I have to keep track of, and I'm going to do this on purpose. I'm going to say that's my positive direction. So I start with, what was B? B was 10. I guess B does look a little smaller than A, but not much. So 10 times minus 15 equals to, add them together, and I get 25 times the velocity 2 of everything hooked together. So what I get is minus 150 over 25. What is that? Equals to minus, okay, we'll do 4, it'd be 6. So the velocity is 6 going to the left. And now he wants to know how determine the maximum spring compression. Now Now you have a new problem. The new problem looks like this. The initial state now is a big block moving to the left at 6 meters per second. And this thing is 25 kilograms. How far does this spring compress? So what you have is 1/2 mv squared equals to the total compression of the spring, K delta squared. There's no loss of energy. Let's see if I can scroll it down. Come on. There we go. And so what you end up with over here is 1/2. The total mass of these things hooked together was that. The velocity is 6. 1/2. The spring stiffness is that. Okay, so let me make sure I write that down. So it's this and delta squared. So that's 5,000. So I don't know what that number is. So what's 36 times 25 divided by 2 divided by 5,000. 0.09. Oh, wait. Sorry. 0.09. Then I got to square root it. Okay. Then it gets to be, why did it not go? 0.3. So delta is equal to 0.3. So this is a case where you broke the problem into two parts. And now I don't even know where I am. Okay. Okay, come on. Okay, where was the problem? Do y'all remember? Wait, no, here it was. Wasn't that it? Okay, F1511, page 243. Let's see if I can find it. Okay, wait. F1511. Okay, so I think that's what I got. So I got the 0.3 meters. And you notice that's kind of what he, okay, so you notice what he did. Then he went to this T and V thing. I don't ever think this way. I mean, I should, but then I just look at the energies of state 1 and state 2. And so with that, now we do one other thing, and that is now, let me shrink this down, see if I have time. I'll start this. Let me find a simple one. Okay, so now we have an impact. Okay, before those two blocks came together, right? And they hit and they stuck. So they stuck together. So let's take a look at this same problem and define what this E is. Let me find my, okay, in this particular case, they stuck together. Let's see. I'll do it like this. So there's this coefficient of restitution, which is called V minus V minus V. In this case, I have A and B. I think he lists them differently. No, he does. He lists them as A and B. And then what he does is the final over the initial. Hang on. So A, B, and then what you find out is they swap places, the final over the initial. And if you look at these, VA2 here, well, in this case, it was 6. But it was going in the left direction. So it was -6 minus 6 over. VB initial was -15, and then minus, this was sitting dead still. If they stick together, the top becomes the same thing, and you get an E of 1. So now let's redo this problem. And this one, we won't be able to look in the back of the book. Let's do the first stage of this problem in which they don't stick together, but say they have a coefficient of restitution. Well, let's do 1 because I know I can do the math easier. How about that? So let's say it's a perfectly elastic image. It's like two super balls hitting each other. When they hit and bounce off each other, they don't lose the energy in the impact. So what happens here? So what you do is you say this, VA2 or final minus VB2 or final. The initial is the same thing, minus 15 minus 0. So I can move this one over to here and get minus 15 equals to VA2 minus VB2. And because I had the coefficient of restitution number given to me, I have a relationship between these two. Now, previously, I made this assumption because he told me to make that assumption. But legally, I can't in general. So if you go in, here, I'll better change colors. So if I go in and take this whole equation with the numbers and stuff and pull it down here, and now I'm working on a different problem. Okay, let me put in the masses as well as everything I know. Well, let me write it once. MA VA1 plus MB VB1, or initials, equal to MA VA2 plus MB VB2. Now, A mass was 15. This was 10. This was 15. This was 10. VA1 is still 0. VB1 is still minus 15. VA2 is unknown. VB2 is unknown. So now let me slide down and try to get a little bit better penmanship, if that's okay. Come on, slide down. There we go. Better penmanship would give me, that's not going to give me anything. This one's going to give me minus 150 equals to 15 VA plus 10 VB. 2 VB2. VBA2. Okay, sorry. Okay, there was a 2 there. So what I have is a defined coefficient of restitution gives me this equation, and this one was given to me by the impulse momentum equation. So now you can see how you can kind of work these out. I can take this equation, stick under here, say multiply everything times 10. So I get minus 150 equals to 10 VA2 minus 10 VB2. So that's this equation times 10. Now I can add these two together. It cancels out the VB2. So now I get, okay, if I add them together, I get minus 300. That's right. That's right. Yeah. And then 25 VA2. So VA2 would be, what is minus 300? Okay, 300 divided by 25 gives me 12. Okay, go away. Okay, so I get minus 12. But VB2 is not going to be that. It's going to be, okay, so if you look back at this equation, this is probably the easiest one to do. VB2 is going to be equal to 15, move that over, plus VA2. Okay, so what is 15 and minus 12? Is that 3? So what happens here in this impact? Okay, it's kind of maybe hard to see because it's kind of tiny, but the fact of the matter is they didn't connect together. This time they bounced off each other and had the same exact energy after the impact they did before. But VA is heading to the left at 12. VB is heading backwards at 3. And if you want to, and I don't know, well, I guess I do have enough time. Let's look at the kinetic energy before and after. What we should find is right after the impact, it here, maybe I should, I don't know. Do we want to do that right now? Or maybe that's too much for the moment. I'll add, but does this part make sense? In these problems, the E is generally given to you. If there's a situation where like the bullet embeds in the block or the two final velocities are going the same, the blocks are connected together, by definition, that's E is equal to 0. Anything else, meaning they're both going in the opposite direction, or they're maybe both going together, but they're not connected together, E varies, is not 0, it's a little bit bigger, but it goes up to 1, and that's the point, and we'll look at it next time. You'll find out the kinetic energy of this with E is equal to 1 before the impact and after the impact is the same. So, you know what? I just got it. Just yeah, the microphone is on. Okay. So, so in essence, you know, this is the coefficient restitution is the one thing that gets added to us that wasn't added in physics. Usually in physics, they stuck there and said, well, the Play-Doh, somebody threw it, embedded in the block, or the bullet shot in the block. They hooked together, something like that, that meant you didn't need this extra equation. So if they're stuck together, that's your extra equation. They're the same. If E is equal to 0, they are the same. So in fact, by E equal to 0, that is the case. Now I could change this to another number, and what you'll find out, you change that to another number, both these velocities change. And so maybe with that, I mean, since we're so close to the end, maybe what I'll do is I'll cover this in the 2 o'clock, and I'll spend, you know, an extra 5 minutes showing them that the energy is the same. So maybe you could look at that, you know, the 2 o'clock thing, and you'll find, you know, it's just the same thing as 1/2 mv squared, 1/2 mv squared that, and then the 1/2 mv squared here and the 1/2 mv squared there. Put them together and you find out that that's the same kinetic energy. It makes sense. That's 15, right? So the m's you add up. Well, that's 12 and that's 3. So it turns out that's they're going to be the same. Or should I do it? It won't take but 5 seconds. I don't know. I don't know if I have the actual energy to do it. 1/2 m MB, what is B is 10 and V is 15 squared. I don't know what that number is. 1/2 10 3 squared plus 1/2. What's the other one? 10? No, it's 15. And 12 squared. Looks really weird. So if I did it real quick, unless I goof up the math, times, say 5. I should have. That's a weird number. 1125? That's a very strange number. So then if I come back here and say 3 squared is 9 times 5 plus, I'll just say 12 squared times 15 divided by 2. It's the same energy. So after impact, it's the same exact energy as it was right before impact. That's not the case with the other one. Here, let's look at the other one real quick. The other one says, that's my initial kinetic energy. This one's for E is equal to 1. For E is equal to 0, they're stuck together. So that means you have 1/2 10 plus 15, and the final velocity there was 6. So if you look at that one, what is that? 36 times 25 divided by 2, or 450. So the energy there was equal to 450. It lost the energy from, it lost 1125 minus 450. So, now in the bullet hitting the block or the Play-Doh hitting the block, the Play-Doh bends or something, somehow these two blocks connecting together and hitting, and somehow their energy has to be turned into like some sort of temperature energy. So in fact, what you find out is with E is equal to 1, it's like a super ball. They bounce off with the same velocity that they started. E is equal to 0, they stuck together. You lost, you went, that's not a 1. That was supposed to be a parentheses. Here, let me get it out of there. Actually, I guess it was the part where I was scribbling at the bottom. So the final kinetic energy with E is equal to 0 is 450, but the initial was 1125. And E is equal to 1, it maintained the same exact energy. So I'm done. We can start over next time. And here along the way, either, I don't know, we'll talk about what the final test is going to be. So maybe in a couple of days, maybe next week, you know.